Okay, next topic is concavity and inflection points. So we say that a function is concave up on an interval if the derivative is an increasing function, and concave down if the derivative is decreasing on that interval. So concave up simply means that f lies above its tangent lines, while f is concave down means that f lies below its tangent lines. So what does this mean? So concave up is something like this, graphically. So for at each point, the function is above its tangent lines, okay? And you see that the slope of the tangent lines at each point is increasing. So this means that the derivative is increasing, okay? So this theorem simplifies this analysis of concavity. If the second derivative is positive on an interval, then the function is concave up. And the second derivative is negative, then the function is concave down. Okay, so this is a concave up function. And conversely, this is a concave down function. So if the function changes concavity, we call that point an inflection point. And if the function is twice differentiable and has an inflection point at x equals 0, at x equals x0, then at that point the second derivative must vanish. Okay. But the converse is not true. If the second derivative is 0, that does not mean that x0 is an inflection point. For example, for this function f of x equals x to the power 4, the second derivative at 0 is 0. But let's just look at the graph. The graph is basically similar to a parabola. So this is y equals x to the power 4. And the function is a concave up function everywhere. So it does not change concavity at x equals 0. Okay, so the vanishing second derivative does not mean inflection point.